And with Brent's technology, I mean, wood is much more forgiving in this sense. It can take that cyclic loading, and it's less likely to crack or plastically deform, and you're not going to break your credit card.
Previously on Shift, we introduced the topic of mass timber with my guests Wayne Classic from C-FER Technologies, who you just heard, and Brent Oland from Greencore Structures. We explored how mass timber is revolutionizing construction, why wooden cores could replace concrete in tall buildings, and how seismic resilience is being built into these structures. Now sit back and settle in for part 2 of From Trees to Towers, the Mass Timber Revolution. Welcome to Shift.
Just for clarity for listeners, we went to, with our particular panel system, we went to loads of 400 to 500,000 pounds in our first and second series of testing at C-FER without any damage to the wood whatsoever. But as with many things from an engineering standpoint, you've got to break it to make it. Mm-hmm. What I mean by that is that you have to establish what the actual overstrength of something is, in order that you can then use engineering calculations that rely on a reasonable rated strength of that material. So in our case, that was the purpose of the third test, was to really pull the material apart in the machine that had the 3.5 million pounds of pulling capability. Clearly the machine's going to win and your specimen's going to lose. And that's exactly what we needed to.
That's the goal.
Mm-hmm. You've got to break it.
Right. Yeah. So C-FER's slogan should be, bring us your stuff, we'll break it. Or we like to break things or something.
The lab technicians certainly enjoy that, but that's not always the outcome of tests that are done there.
Yeah, it's been described as a real world version of Mythbusters, I think, a lot of times. So it's
right.
It's sort of an independent consumer reports, and then put it through its paces and really find out where the limits are. I guess that's a good maybe segue to the full scale testing and the value of full scale testing. Getting back to your earlier question, John.
Yeah.
Like evaluating where those weak points are in a system is actually something else that I would say is very, very common to, like, it's cross industry. It doesn't matter if it's airplanes or it's, nuclear components. You need to do those full scale tests and really stress the technology. And sometimes, like in this case, you find out that the base technology, the lumber in this case, was, much, much better than you first thought. So it's some other component that you identify. But because you do the full scale tests and it's very controlled and it's under this range of conditions and you've got a lot of instrumentation, you can diagnose exactly what happened. And that informs the next design and the next design and the next design. And that's how the technology improves. It's that iterative, scientific investigation.
Right. And all of that data, that's the data that you acquired from doing all of these tests, that goes back to Brent and Greencore, no one else.
Exactly right. That's the independent, that's the third-party consumer reports aspect of this. So C-FER really doesn't have a place when it comes to commercializing technology we're here to support good applied research. We're here to support companies like Greencore, like industry. We don't build things ourselves. We don't own oil wells or airplanes or build construction towers. We're experts at testing technology. So that's really our jam.
Wayne, come on, say you're experts at breaking things.
Experts at breaking things, yes. We do enjoy it.
I'm just curious now, when you guys were testing and stressing this material, I would imagine when a piece of wood breaks, it's pretty loud. There's quite a snap. What was that like? Was it, the sound and the visuals of it coming apart? Was it really loud? Did anybody shoot video?
We did, and actually, it's a good point you made. So we actually took acoustical measurements in some of the early tests too, to identify when the failures were happening, and we're trying to sync up the loading and the stresses that we're putting the technology under with the video and the audio, so that we get a good representation of what's happening. I guess testing wood did have some unique considerations in that sense, and I mean, C-FER does 150 or 200 unique research programs like this a year, and they all have their own challenges. But the structural testing of wood, you can imagine, like we had more considerations around how will this fail? If it failed, what sort of safety barriers do we need in place? What sort of things do we need to make sure that we're being safe? And that could be shrapnel from the test specimen when it flies apart. It could be acoustical damage. Like it's a funny thing actually, but a lot of the tests we do, they do make a lot of noise when you rupture a big pressure vessel or you break something, very aggressively. So we think about things like, what are the decibels when this test specimen might break? How do we make sure that everyone is safe in the environment?
Right. No, that's really cool. One thing I didn't ask you about, Brent, is now we're building these mass timber structures. When you think about fire is no good. How do you mitigate any sort of concern with fire? Well, I know you can't completely get rid of it, but how do you mitigate that if someone goes, well, my concrete's not going to burn?
I think we should have listeners understand that there are three different considerations with regard to fire and wood in buildings. The first one is charring, and the softwood lumber that our forests provide has a very consistent pace of charring, is actually 0.65 of a millimeter per minute. And that gives kind of a thickness of wood that you would need in order to provide, say, 1 hour or 2 hour worth of fire rating. That's the first consideration. The second consideration is what's called flame spread rating, which is if you have a flame under or climbing up your surface, how fast can that flame spread along the surface? And the third item is smoke development rating, which is if your material is burning, how much smoke is it producing? What we have to do in the structural engineering side primarily doesn't worry too much about the flame spread rating and the smoke development rating, but rather is governed around the charring, because what we're looking to do is have the majority of a structural member still strong and useful, even if part of it is burning. So I want listeners to think of burning a piece of dry grass compared to burning, say, matchsticks, compared to burning kindling, compared to burning like split firewood, and then compared to burning a big round log. Mass timber is mostly like in the category of the big round log. So, if you've put a log that's too large in a wood fire, 2 hours later, it's still mostly there. That's how mass timber is with these technologies that we're using with this material. Greencore's material in particular is more like plywood than cross-laminated timber. And plywood doesn't burn as well as cross-laminated timber does. As a matter of fact, if you took our panels and we wanted to bet, a couple cases of beer on whether you could get the flame to go and self-sustain, if it all you have is one surface of the material and there's no heat reflecting second piece of material nearby, you can stand with a tiger torch on that material and it will char and it'll blacken and it'll smoke and there'll be some flames. When you remove the tiger torch, what actually happens? It goes out, because it's combustible, but it's not flammable. So if you look in construction at conventional wood frame or what we call stick frame construction, those buildings are nearly flammable compared to a mass timber building being just combustible. So we have hours of durability typically of the core elements of the structure in a flame condition. And in fact, the buildings are designed to accommodate the fire burning the contents of the building more so than the structure. and effectively just burning itself out. That's the design basis of it. You design the structural members to stay competent long enough that whatever was on fire within the building, contents of the building, just gets consumed and burns itself out. And after that, the structure is still standing and still able to support loads.
Right. So, Brent, you're putting all this technology together. You're building this product. You go, we need to now subject it to these tests. How did you know about C-FER?
C-FER was a referral from the University of Alberta. My first approach when we needed to do these tests, and we understood that the loads were going to be large, although frankly, in hindsight, we didn't understand how large. They were even larger than we understood. But the loads that we expected were already too large for the facilities that were existing at the research universities in Western Canada, whether it be Vancouver or Prince George or Calgary or even Edmonton. The universities themselves did not have such a facility like C-FER offers to be available to react to loads. You know, they say every action requires an equal and opposite reaction. Well, certainly that is exactly the case. What we're talking about during this testing, you know, whether it's the frame of the universal testing system or UTS tension testing machine or the strong floor that's 6 feet thick, what happens at the testing lab is you're creating a reaction within elements of the lab itself. Then you're using links and hydraulic elements in order to anchor to that strong part of the lab and impose forces then into your specimen, which have opposite forces within the permanent parts of the testing lab. So the construction and the configuration of the lab itself was of a greater and stronger scale at C-FER than what's offered at any university in Canada. And in some cases, their equipment and their load capacities are among the top few facilities in the world.
To both of you, we'll wrap this up right away, but I want to know what's next, Brent, from for Greencore and the mass timber technology. What's next for you guys at this point?
The fundamental question at hand is how many stories are we allowed to use Greencore's core system while not exceeding interstory drift criteria or other criteria of allowable displacements. And knowing, of course, with our system, it's going to also recenter after force application stops. But we need to stay within the engineering parameters of displacements. And so what happens is there are other variables like the degree of seismicity of a particular project site location, whether that's Langford, BC, or Kelowna, or somewhere in Alberta, or Ottawa, Ontario. There's all these different places that have some seismic concern, or a few places with severe seismic concern. And so what happens with our building system is it can be used to a taller number of floors in a non-seismic or low seismic area, and a lesser number of floors in a high seismic area. But the exact number of floors of that is only able to be determined through structural dynamic modeling, which relies back to all of the output of the various modes of testing that the products were subjected to at C-FER. So it ends up very real world, ends up very accurate. You can't fake these things. You have to test them. Nobody can use their professional opinion as a substitute for actual testing.
Right. So you're taking all of this data that Wayne and team have garnered from all of their tests on your product. You're taking that data and then feeding it into a computer model and going, how high can we go in a high seismic area? How high can we go in a low seismic area?
That's right.
So if you were to ballpark it, just spitball a number and say X number of years or months to go through all of this and to start getting Greencore built, buildings that are using Greencore, how far in the future is that? Everything works out.
We found our feasible material in 2021, and we have about a year left in our process right now, so by early 2026. So developing something like this is about a 5-year process.
Okay. Oh, thank you. I feel like I've learned a lot in terms of the pathway, the life cycle of engineering products like this. So thank you very much for the details. Now, Wayne, from a C-FER perspective, what's next for you guys? Now, I understand you've wrapped up with Greencore. Maybe there's more to come down the pike with Greencore. What's the next big project you guys have?
We've got a few, and I mean that's the, I guess that's the nature of maybe the work that we do. So we get to see a very interesting part, but I think maybe in some ways a small part of the technology development. So what Brent has just detailed is common. Performance-based testing is crucial. He's done this rigorous evaluation of his technology. He's built this new informed simulation that he can use to show the engineers and the general public that his technology is safe and he can use it. C-FER is here to support it. In the future, Greencore may come back. There may be other technologies like it that need to be validated. Our place in this development cycle is to really help do that performance testing on these, that full-scale test, that careful experimentation on this technology. Like I said at the beginning, we don't build the towers ourselves. We don't own the construction process, but we definitely are very interested in seeing it develop and support. I think we get to work in a lot of different industries, and building technology, green building technology is important in Canada for a lot of reasons, but I think there's a big opportunity for us. There's a housing crisis that I think a lot of people are aware of. So the faster that we can build high quality, affordable, low carbon buildings, I mean, there's so many benefits. So I guess we've been blessed to be involved with it. C-FER team, like I said, is working on a couple hundred projects a year. We're in all sorts of stuff right now. So earlier this week, we were talking about some cryogenic tests at super cold temperatures. We're actually looking at some high multi-phase flow tests, nuclear industry, aerospace industry. So it really is, it changes minute by minute, but Greencore has been a really interesting one.
Keeps you guys busy.
Mm-hmm.
What I'd like to wrap up with is why are we doing all this? Greencore exists to improve the availability of housing. That's what our actual purpose is. And in the construction industry, the productivity has been famously poor. Like the actual productivity of construction now is as or worse than it was in 1960. And we believe that the only
define
way...
that.
What's that?
Sorry, Brent, define that, our productivity. Do you mean...
Well, you've got a crew of guys and they're trying to build a certain number of square footage of housing. They actually build less square footage per worker per year now than they did back in 1960.
What accounts for that?
Well, training for one thing. Our construction workforce doesn't have training anymore. Regulation for another thing. All of the restrictions and regulations about how you can build buildings has made buildings fundamentally more complicated every year. And the simplistic structures that used to be built fast, in decades past are not allowed for reasons of energy efficiency or seismic resistance for one thing. Our buildings are demanded to be far more complex now, to be structurally more capable, building envelope more capable, efficient energy usage and distribution systems. The level of complexity of construction in general is orders of magnitude more than it was in 1960. And what it causes is that a certain number of workers can produce and deliver less housing now than they could at that time. So Greencore believes that we have part of a solution. We believe that the only way to change how we build as an industry is to change what we build with. And by what we build with, I mean typically larger but fewer number of components and construction processes that instead of labor and workforce driven are more crane driven. These are ways of enhancing productivity so that the number of workers you do have available, which I think it's well known, construction has a severe workforce shortage. And then within the workforce it does have, it has a severe skills shortage. I'm not going to sugarcoat that. The way around that is to use more machines and less human effort. And the way for that is to have bigger but tested and reliable pieces that are installed with cranes. And so that's exactly what we're doing. We're comprehensively envisioning buildings that are panelized into large pieces for the structure, the building envelope, and in our case, even the core system, so that all of those pieces use less crane time, so that all of the crane time that is available can make the building progress very rapidly, far more rapidly than could ever be produced using a labor-driven construction process. So we're basically taking labor out of housing, like we're reducing the amount of labor needed to produce housing. And that's important, because if you have a certain number of workers and certain available skill set within those workers, those people that are available, those men and women of the construction industry, can produce far more housing if we give them better pieces to build with.
Yeah, you're not limited anymore by the capacity, right? So very noble.
We're going to have projects with faster construction schedule, lower carbon footprint, lighter weight buildings, cleaner construction because most of the waste is produced off-site and it's properly recycled, quieter construction because we're not chipping and chiseling and sawing things on the job site, which would represent poor planning, safer construction because we're eliminating dangerous tasks or tasks that might be done at heights are instead done in the safety of an off-site fabrication shop. We're making buildings that help people's health because they feel better and lower stress when they see wood in their building. And we're also creating buildings that, because of all of the large panels I mentioned, can be taken apart at the end of the serviceable life of the building and can actually be relocated or reused or if not, at least recycled. This is far better from a environmental impact standpoint than the conventional materials. So we have all these possibilities at hand, improve productivity, improve the availability of housing, improve the timeline and the economic output of a project, improving, like, from a financial standpoint, net present value of a project. Well, if you get your project sooner and the rent starts earlier on, say it's rental residential, months earlier, you're saving time on the construction, which saves money, saving time on the financing, which saves money, and then you're producing rent months earlier, which creates new rent that wouldn't have existed with a longer duration of project. These are really valuable things, even aside from the reduced environmental impact. So there's a lot at stake here.
Yeah, this is a real shift, and I think it's great that the work that's going on. Guys, let's leave it at that. I think there's a lot to chew on here. It's fantastic work you're both doing, and thank you very much for your time. I appreciate it.
Nice talking to you. Thank you so much.
Yeah, thank you, John, and thanks, Wayne. We'll keep our collaboration going.
Shift is brought to you by Alberta Innovates. We can be found online at shift.albertainnovates.ca or shift@albertainnovates.ca if you want to get in touch. Have a great day. Thanks.